Okay, and welcome to a recording on picture patterns of quadratics. Now, this first pattern we did in class last time, but this pattern shows us that the figure 1 here is a 1 by 1 square. This would be a 2 by 2, and this would be a 3 by 3. And if we called this figure number 1, figure number 2, and figure number 3, and that was our x values, then our y values would be the number of squares. And remember, we made a table. Okay, and I'm just going to make this table again. It should be in your notes. And we had x here and y equaled the number of squares, and x equaled the figure number. Okay. And if we made a table for these, well, figure number 1 was 1 square. Figure number 2 is 2 times 2, 4 squares, or you can count them. And 3 times 3 is 9 squares. And if the pattern continued, then it would be 4, 16, 5, 25, and 6, 36. And we explored last class that the first difference here is increasing by 2 every single time, which shows that this first difference column has a linear pattern. And the second difference column is constant. And that tells us that we have a quadratic function. And the equation for this quadratic would be if we changed these dimensions, which we know are 1 by 1, to x times x, because if we plug x in and our x value is 1, that is the same as 1 by 1, or 2 by 2, or 3 by 3. So our equation that we came up with last class was y equals x squared. So whenever you see this pattern of a square increasing its dimensions by 1 each time, from a 1 by 1 to a 2 by 2 to a 3 by 3 square, our equation is x squared because x times x equals x squared. Okay? So that's the foundational principle of quadratics. Now, throughout this lesson, you can take notes on whatever you feel like you need to take notes on, but I think the best thing to do is kind of just watch, try and solve these problems with your group, and come up with an equation, okay? So let's try another one, and I'm going to manipulate this picture to have an extra box up here. So we got one extra box here. We'll say we got one extra box here and one extra box here. Now, what would the equation be for this? Well, we still see our normal quadratic pattern of this square increasing its dimensions by 1. So we know the part in red is x squared. Well, how do we fix this equation so that it resembles this additional square up here in green? Well, that's one extra box in each image. So that's a constant. So we would just say that's plus 1. Okay? Now, we can, check to see if this is indeed true. If you plug, this is figure number 1. If we plug 1 in for x, we would say this is 1 squared plus 1, and 1 squared is 1 plus 1 is indeed 2 squares here. If we plugged 2 in, this is figure number 2. Plug 2 into the formula. 2 squared plus 1 is 4 plus 1, which is 5 squares. Looks good. And this is figure number 3, which is 3 squared plus 1. 3 squared is 9, plus 1 is 10. Okay? So that indeed does work. So there is our quadratic equation for this picture pattern. Okay. Now I'm going to do one more. Now this time I'm going to add let's just put it down here this time. We're going to add a box down here. And then we're going to add 2 boxes. And then we're going to add 3 boxes. Okay. So again, you should see, okay, we've got this original pattern in red, which we call x squared, okay? But how are we going to write an equation for this additional stuff? Well, it goes 1, 2, and 3. Well, what is that related to? Our figure number is 1, our figure number is 2, and our figure number is 3. And hopefully you notice that is our x term, okay? So it's increasing by a value of x. So we would just say plus x, okay? Now, building on this idea, what if I said we had another box over here, and another 2 boxes over here, and another 3 boxes over here? That would be increasing not by 1, 2, and 3, but increasing by 2, 4, and 6, right? Well, my x value is 1, 2, 3. But this is increasing by 2 every time. So what would we have to multiply our x value to get that? Well, 1 times what is 2? 2. 2 times what is 4? 2. And 3 times what is 6? 2. So we'd have to multiply x by 2. So what would I have to do to manipulate this equation? I would say plus 2x, because that's a linear change occurring. It's increasing by 2 more each time, in addition to that x squared pattern we see in red. Okay, so this would be the equation for this pattern. All right, let's do, I think you guys are good on that. So again, this original pattern you're looking at is y equals x squared. Now let's go try this problem. And this problem looks like it's got this picture right here, but there's a square eaten out of it. There's no square here. There's no square here. And in theory, there's no imaginary square. There's no imaginary square here either. Okay, so what would our equation be? Well, it's forming that same pattern we had up here, but we're short 1 box on each figure. So our equation would be y equals x squared minus 1. All right. Now, hopefully that makes sense. We could plug these numbers in to see why. Like if this is our x term, well, we would plug 1 squared minus 1 in, and that would yield 1 minus 1 is 0, which was empty, right? No boxes. This would be 2 squared minus 1, which is 4 minus 1, which is 3. 3 boxes. And we'll just prove it. 9 minus 1 is 8 boxes, okay? Let's move on to this one. And I actually want you guys to try this one on your own right now. So I'll pause for a second here. You can even pause the video if you'd like. And try to find the equation to this picture pattern. Now, if we were just looking at the part in red, I hope you would all say, all right, we've got y equals x squared, okay? But what would you have to do to the rest of the equation to make it true? Well, we've got these 4 squares on the outside that show up on each figure. So on each figure, how many extra squares do we have? We have 4 extra on each picture. So to the equation, we would just have to say, oh, it's x squared, it's that red stuff, plus 4 squares. So if you got that, fantastic job. And if you did make a table for these, I haven't been making a table for the last few, but if you did make a table, let's make a table out of this one. This would be 5, this would be 8, and this would be 13. And if you see the difference between them, the difference here is 3, the difference here is 5, and the next difference would be 7. So how many would be in the next picture? Well, 20 would be in the next picture. And because this change that you see in green here is linear, we know it's a quadratic. The other reason we know it's quadratic is has that x squared term, okay? All right, let's move on. Now I'm going to pause again, give you a try to do this problem. And this is a little trickier, but I think you can do it. We'll call this figure number 1, figure number 2, and figure number 3. Now it's pretty obvious that we can't just say this is x times x, because 1 times 1 is definitely not how many squares we have here. It looks like we have 16 squares here. So this is a 4 by 4, this is a 5 by 5, and this is a 6 by 6. So it is true that these are squares, so we should have a quadratic function here. But how am I going to manipulate this side to equal 4? Well, if x is 1, because this is figure number 1, how are we going to go from 1 to 4? Well, we'd have to add 3 to this side of the quadratic. And we would have to do the same thing to this side, x plus 3. And if you multiply those together, that would be x plus 3 times x plus 3, which is perfect, okay? And we can see if that works. If you plug 1 in for x, well, that would be 1 plus 3 times 1 plus 3, which is 1 plus 3 is 4, times 4 is 16 total squares. And that's how many squares we had here. And we can try that with figure number 2 as well. If you plug in this same formula for, well, for when x is 2, 2 plus 3 is 5, times 2 plus 3 is also 5, which equals 25 here, okay? So that's what our equation is. So I'll write it up here. Y equals x plus 3 times x plus 3. And a way to simplify this is you just make an exponent there, because they're getting multiplied by themselves. Alrighty. And if you did make a table, like this is 16, this is 25, this is 36, what would the next one be? 49, and you'll notice that pattern is increasing by 9, 11, and the next one would be 13. So it's got that linear pattern, which means it's a quadratic function. Okay. I think you're okay. Maybe we'll do this one. This is a solid problem, and then we'll end the video after we do this one. So do your best to solve this. It's a little tricky. Okay, so I've highlighted the extra 2 squares I see in each figure, okay? And remember, this is figure number 1, figure number 2, and figure number 3. But the dimensions of this are 1 by 3, 2 by 4, and 3 by 5 of this rectangular image in the middle, excluding those 2 pink squares. Well, how could we do the dimensions of this rectangle? Well, we haven't talked about rectangles yet. Or have we? Have we talked about rectangles? Did we do that up here? No, we have not. So this is a good one to talk about. Fantastic. Well, if we have a rectangle, and this is increasing, okay, 1, 2, 3. That looks just like our x term. So if we were finding the area of a rectangle, we would do length times width. So this side is definitely x, okay? The 1, 2, 3 part. Now, how would we do the other side? This says 3, this says 4, and this says 5, okay? Well, how many more is that than our x term here? And our x term is 1. Well, how do we go from 1 to 3? We would have to say x plus 2. How do we get to 4? Well, if my x term's 2, then we would say, again, 2 plus 2 is 4, so x plus 2. X plus 2. So our equation here, for the dimensions of at least the rectangular part, we would say is y equals x times x plus 2. And then we'd have to add on that constant 2 squares that you see on every image, so we'd have to say plus 2 at the end. And if we were going to distribute or simplify this expression, we would distribute the x in, which x times x is x squared. X times 2 is 2x plus 2. And that would be an equation written in what we call standard form, which we'll talk about a little bit more. And this brings me to some more notes I could talk about. Probably not good to do on this problem, but we'll just leave it at that, and we'll discuss this more in depth later. I'm just going to see if there's any more good ones here to talk about. Why don't you guys try this last one right here, okay? So this picture pattern, and I'll give you like 30 seconds to try to come up with an equation for this pattern. Okay. Now, I hope you notice that we're missing a little chunk here. I'll put a little imaginary, whatever these are, I'm going to call them marbles. Missing an imaginary, marble in each one of these pictures. Now, imagining that marble did exist, we'll just say it exists for now, what would my equation be? Well, it's not x times x because our x is 1. We have to increase our x by 1. So this would be x plus 1 times x plus 1. So x plus 1 times x plus 1, which can be rewritten as x plus 1 squared. And then what are we going to do? Well, we're missing one of these from each figure. So we would subtract by 1. And that would be our equation. Put y equals in the front, or f of x equals. So hopefully this kind of makes sense on how you can manipulate picture patterns to write quadratic equations. And hopefully this helps you with your homework a little bit today. So for the rest of class, you can finish or work on the 2.2 homework. It's a little more difficult, but it's not that many questions, so help each other out, work on that. please show your work in your notebook. It's always helpful to make tables uh, and and try to identify specifically these x squared patterns that we started with. Okay, so this first pattern right here, you're looking for this, and if you ever see this pattern right here, you know it forms an x squared term. And if it's even close to that pattern, think about how you can manipulate your x squared to make it work. Okay, so hopefully this was helpful. Excited to see you guys all in class on Tuesday next week.